Okay, today we'll continue with the last lecture. That means we'll continue with MATLAB code to solve the stress and deformation analysis. First, we'll calculate the principal stresses that we had already calculated. That part we did earlier. So that earlier version of our MATLAB code, we have named it as version 1. Okay. So in version 1, how far we did? We calculated the traction vector. Okay. And that much we did. Now today what we'll do, we have added another module which was to determine first the principal stresses. Okay. Now regarding this determination of principal stresses, what we have mentioned is that, say this is a particular way of finding principal stress. So this is a problem. Okay. This is the state of stress matrix given. As you know, to solve the principal stresses, first we need to find out the stress invariants, and from there we form a cubic equation. Solution of the cubic equation gives us the principal stresses. Okay, detailing is not shown here as such, but associated with each of the principal stresses, there is a principal direction also. Now, one of the method we mentioned is that if we find out eigenvalues of this matrix, that would give the principal stresses. Second one is the solution of the equation through numerical method. Solution of the equation means this particular equation. Okay. Through numerical methods, we can solve it. But before going to that numerical method, which would be approximate, let us see this particular method where we have an analytical solution. Okay. So this is the method, analytical method to solve a cubic equation. Okay. Now the general form of a cubic equation is like this. Okay. Now you note this is our cubic equation, right? So if we compare this one with the general form, for our case A is 1, this B is minus I1, C is I2, and D is minus I3. So if this is the general form of a cubic equation, it is possible to reduce that equation in this particular form. Okay. Now, when it is possible, there is a condition. Only when this P and Q, what are this P and Q? They are given here. Okay, from the given equation, this is, if this is our equation, we know what is A, B, C, D. We can find out what is P and what is Q. And then, if this is the condition, then the given equation, this general form, can be reduced to this, where P and Q are given in terms of A, B, C, D. That is clear. Now, this quantity is called discriminant of the cubic equation. So, if this is greater than 0, in our case, you see this P and Q, they will come as negative or something. So, our case will be this one. We have 3 unequal real roots. Okay. And what are the roots of this particular equation? This particular equation we are getting from the general form of the cubic equation. So our cubic equation first have to be expressed in this form. So that means we have to find out what is P, what is Q. And then with that, we know the three equations of this particular equation, right? So now our equation, this equation is in this form. The three roots of this particular equation is given by this, okay? Here you see, these roots, T1, actually they are T1, T2 and T3, okay? So they are in terms of unknown A and this angle phi, right? So you see this phi is now given in terms of P and Q. This P and Q we know. Similarly, this A, this constant A, this is also known to us. So this one is the analytical method which we will follow. This is arc cos means cos inverse. Okay. So this is what we will follow in our MATLAB program. Okay. There are other methods also. We'll also use eigenvalue analysis to make a solution of that. We'll see it. Okay. Now there is another part of it. Given a stress tensor, we can find out what are the principal stresses. And then there are two more quantities which are of interest to us. Those two quantities are called sigma and tau. Actually, they are sigma and tau for this particular plane, right? Hmm. So, so you see, we have a particular direction cosine that we have already used. Now, for this particular plane where outward normal is n, we can find out a component of stress along n direction. This is sigma. And T is our traction vector, which is the resultant vector for this particular state of stress. Okay. So component of T is along n direction and another component is along this plane. So that would be our shear component. So that we have seen this T square is equal to sigma square plus that tau square. But determination of this sigma and tau, that we should find out also. Now you see this sigma, how to determine this sigma? Let us see this. Okay. First is how we find out T, that we already did in our program also. From the given state of stress matrix and from the given direction cosines of the particular direction. Okay, for this plane, the outer normal direction is given by nx, ny, nz. We calculated these components from the Cauchy's equation. And if we find out T, which is basically the square root of the sum of these square quantities. Okay. Then we can get component of this T vector along outer normal because our sigma direction is along outer normal. Direction of T is somewhat different. It is not along the outer normal. So if these two directions are identical, what we get is the principal stress. But in general, this is not the case. So that way, this sigma we can find out from this equation. Okay, what it is? Component of Tx along direction n, this component of Ty along direction n, outer normal direction, and component of z. So then if we substitute for these components, we get this is our equation for this sigma, we define it as sigma suffix n. Okay, normal stress, and another component given by this tau. Okay. So T square is sigma square plus tau square. This we can compute as the square root of this T square minus sigma square under root is this tau. Tau n. We say this as tau n and this as sigma n. So this is what we'll also calculate, and then let us see another method. So we know how to calculate sigma, right? From the components of T that we can calculate. Once this is known, we find out this tau as well. But there are another method. Let us see to it. This is not the thing. Yeah, this one is the method. So you see, this T has a direction, right? If we determine the direction of this T vector, that means our traction, then what happens for this direction T? We have direction cosines. For this outer normal, we have direction cosines. Actually, this is given. This is a priori known to us. Now, from the direction cosines of two lines which are intersecting, okay, here they are passing through the same point, okay, then the angle between these two lines are given by this particular equation. This comes from analytical geometry. So you understand what it is? Say the angle between PQ and PR is theta. Then cos of theta is, say this is our line 1, this is our line 2, and their direction cosines are nx1, ny1, nz1. For line 2, nx2, ny2, and nz2. What is theta? Cos inverse of this quantity. So now note here that this idea we'll use afterwards to compute strain, angular strain. Okay. So if these two lines change their position, and the changed position is represented by this prime q prime and p prime r prime, and say in that situation the included angle is theta prime, then this equation holds. If we can track the change in direction cosines of these lines, then again nx1 prime, this ny1 prime, they are also known. So that is one of the way of calculating angular strain. So what we are measuring here, change in this included angle theta, and therefrom we calculate shear strain. We'll use it afterwards. But right now, we'll use this particular equation, say the first one, to find out the angle between T vector and our outer normal vector, N and T. So if this is known, what is sigma? This component of T, if we project T on this direction, we will get sigma. Simply T cos theta. What is T? This tau. This is sin theta component. So these two calculations, if we calculate sigma from this component of T along N, this will give us sigma normal. And previously also we calculated sigma normal from the components of this T vector. They should be identical. Okay. That is also what we will do in our MATLAB routine. Okay. So this is what we are going to do now. Let us see this MATLAB program now. Okay. So once again, this was our earlier version, right? So what we did here, we calculated the components of T vector. This was our components of T vector. Clear? In the next version, what we did, this is the one. This much we did, we calculated components of T vector. Then this is T. Okay. So this T vec, these are the components, and this capital T is square root of the square sum of this component. So this is T. Now you see, what is the direction cosine of this T? If we divide the component of T vector along xyz with this T, we'll get the direction cosines of this T along x, y and z. So they are indicated as nxt, nyt and nzt. Clear? Previously, we had direction cosines. This was input. We got it from the user. And now we have calculated these direction cosines of the T vector. So it has three components, this nxt, nyt and nz. Clear? Very clear. So from this direction cosine dcn and from this dcn t, we can calculate the angle. So this is what we've done there. Yes. Let us calculate cos of theta. So cos t, so this cos t stands for cos of theta. This is what we have already seen. The nx1 into nx2, here it is nxt into the first component of this here. This is clear? Cos theta is equal to this, right? Now, what is sigma n? This is our sigma vector. Right? So principal stress along outer normal direction, sigma n. Is t into this cos theta, clear? And what is this tau value? On that given plane, it is square root of t square minus this sigma n square. So we got sigma n and tau n from the first method. Yeah. Now there was another equation for that. If we take component of t vector, okay, along outer normal direction. Okay, this is first component of t vector tx, and this is nx. So that is also we have seen. So this Sn stands for, again the same thing, this sigma n, but calculated from another method, that means from the components of T vector. Right? So this Sn and sigma n, ideally they should be equal. This is what is displayed here also. What is sigma n and what is this Sn? They should be identical. Clear? Okay, this is what is there. If we run the program, we can see that this will happen. Let us see some more components are there. What it is here. Here we have calculated the principal stresses as well. Right? So this PS stands for principal stress. So to determine this principal stress, what we have used? Actually, we have used that analytical equations. We have just mentioned what are those analytical equations. Okay. And that is calculated in another function which is find PS. Okay. Let us go to that find PS. Clear? Previously, this function we have seen earlier. Then we had then this is our function. Okay, this function find PS, name of the function. It has an argument. What is the argument? S is our input stress tensor, right? This one we get from this input stress routine. Earlier, this is known, and that given stress tensor, they are stored in this variable S. So find principal stress requires that stress vector. So this is the argument. What is the argument? Output of this particular function? It gives PS, that means principal stress. So obviously this PS has three components: sigma 1, sigma 2, sigma 3. Those are the components of PS. Now, to calculate principal stress, first one is calculation of I1, I2 and I3. Right? I am not going back into the theory part once again, but this is what we have discussed. To know how to determine this one, we expand the associated determinant of this stress tensor. And from there, we solve that cubic equation. Before solving it, first we get the coefficient of the cubic equation. From there, we get I1, I2, I3. You follow the theoretical equations and just check whether they are correct or not. Next, what? In analytical solution, we require two quantities P and Q. Okay, and let us form that. Actually, they are named as A and B here. Okay, and for ease of this coding, this I1, I2 and I3, they are renamed as minus I1, then this is I2 and this I3, so that the generalized equation, okay, we get in the standard form. Okay. So that you have to find out of your own, right? So here, this A and B are those two quantities. 3q minus b square and this quantity, okay, divided by 27. They are the P and Q of the analytical solution. These are A and B. 0.5, this divided by, actually you see this dot is necessary here. Why? This indicates that this is a real number, right? You know about integer division and the real number division. Okay. Similarly, this 27 dot indicates this is a real number. Okay. So it comes from there. You see, these dots, they come from there. Okay. just to indicate those are real numbers. Actually, what I think, this is what this particular MATLAB editor, it will take care of this thing, because I didn't make those dots. So after running the program, I noticed these dots have come. So that is the thing, right? So what next? Afterwards, we have to find out that phi cos inverse of this one. Okay, let us go there once again. What was our equations? These were the equations. So this P and Q is now named as A and B. Okay. These coefficients, they are named as, these are named as P, Q and R. So in terms of that P, Q and R, this is now A, this is now B. Okay. And accordingly, from this A and B, this angle phi and this quantity A, it is calculated. This is fine. So this is our phi cos inverse of that, and G is that capital A. In analytical equation, we had capital A, here it is a G. And these are the three roots. These three roots are named as S1, S2 and S3. So they are the principal stresses. Here cos phi by 3, then there was this plus 2 pi and this plus 4 pi. And this is our principal stress. These three components are clubbed together in an array. Right. So these directions, there would be three sets of directions, right? One for S1, one for S2, one for S3. That is not calculated as such. Here, this, we can calculate that also. So this is the end of our subroutine. So from there, we'll get this principal stress. Okay. And what is done here? This summation of principal stress, this should be equal to the diagonal terms of our stress matrix. Okay. Next, the eigenvalues of this S matrix, they are also calculated. This EIG is an inbuilt function. Okay. So you can see this thing, it will give you the eigenvalues. So these three eigenvalues are again stored here in principal stress from eigenvalue analysis. So this is PS. This is from analytical calculation. Find PS is the analytical calculation. This is directly eigenvalue analysis calculated by the inbuilt function EIG. You can write this thing, you will see this will give you something on EIG. You can make a Google search as well, help EIG rate. Okay. This is what it is giving. EIG gives eigenvalues and eigenvectors. E equal to EIG A produces a column vector E containing the eigenvalues of this matrix A. So this is what we have used. This eigenvalue analysis part in MATLAB is very easy. Just a minute. কি বলছে?